In the name of Allah, the most beneficent and the most merciful. Perhaps we were here. We had made discussions on the design of irrigation channel by using the regime method, and now today I would like to start the design of channels by rational method. So you know that in this rational method, dimensions of the channel. What are the dimensions of the channel? The depth of flow, bottom width of the channel, side slope, top width of the channel, and the longitudinal slopes. These are determined by considering the basic principles, the basic principles of hydraulics for flow of water and sediment transport under dynamic equilibrium. Rational method. So we do not have a data of so many stable channels, and then we have derived relationships, and using those relationships, it is not like that. So we have to simply design a channel on basic principles of hydraulic engineering for flow of water and for sediment transport. So canal sections will be stable if the velocity of flow in the channel is such that all suspended sediment which are entered in the canal, those remain in suspension and those passes away at that particular section. And at the same time, the velocity is such that it is not moving any sediment particle which is on the bed or sides. So it means such a channel will not cause the scouring, neither the silting, which are the two main problems in the alluvial channels, or the unlined channels or earthen channels. So what are the two major problems of the earthen channels? Somebody should tell me. I am asking you.
Scouring and sedimentation.
Silting and scouring.
Yes, very good. Silting and scouring. Yes, you can say sedimentation as well. Sedimentation or silting is the same thing. The sediments they may deposit on the bed of the channel, whereas the scouring is another. The main the challenge in the design of alluvial channels. Now, if you see the sediment load at any section of the channel, it can be divided in two major components. One is the bed load, and the second is suspended load. And we have already discussed bed load in the hydraulic engineering subject, and there was a chapter sediment transport. So bed load is that part of sediment load, these are those sediments which moves in contact with bed in the channel. And the contact with bed could be in three ways. Maybe a sediment particle is rolling on the bed. Secondly, it may slide on the bed. And thirdly, it may move in hooping or saltation. It means the sediment particle is being lifted up and then again dropped. Anyway, it moves in the downstream direction continuously in contact with the bed. That is called as bed load. Whereas the another is suspended load. Suspended load means those sediment particles which they are in suspension due to sufficient turbulence, and if we add both the bed load and the suspended load, then we can get the total sediment load which is moving in a channel or in a stream at a particular section. Is it okay?
Yes, sir.
Okay, now we have separate functions. What do you mean by functions? When I say functions, functions means equations. Functions means models. Functions means formulae. So we have separate formulae for bed load to compute the bed load transport rate and to compute the suspended load transport rate. Though we have equations as well, and we can also measure the bed load in a stream or in a channel, and this suspended load we can also measure. So it means we can measure it, and we have the functions also to compute it. Is it clear? Okay, now these equations which are for bed load and suspended load, on what basis these equations were developed by the several hydraulic engineers? And they have developed these equations. These equations are basically empirical in nature, and these equations are developed by taking a laboratory experiment data. Okay, so there were several experiments were carried out in the labs, and from those data these equations were developed, and also some field data wherever it was available. So that was also used to compute the to derive these equations for the bed load and for suspended load. And I think in the subject of hydraulic engineering in 7th term, we have discussed few equations. All right. Now we want to discuss what are bed load transport functions or formulae or equations. You know, there are many bed load equations, bed load transport equations. Those equations by which we can compute bed load transport rate. But these four I have mentioned here, which are very common and widely used to compute the bed load transport rate in channels. The first one is Dubai's formula. The second is Einstein's bed load formula. The third is Einstein-Brown formula. And the fourth is Mayer, Peter, and Muller formula. However, you know, even more than these four, there are many. We have equations to compute the bed load transport rate. But none of the formula has gained general acceptance. You know, if you will use these formulae, they will give you the drastic different results. And these above formulas, in combination with Manning's and other formulae, they are used for design of channel by rational method. So the first formula which we want to discuss is the bed load function or Dubai's formula. Okay, the Dubai's equation to compute the bed load transport rate. And you know, it is one of the oldest method in use. This is the oldest formula. And in this Dubai's, how he has derived this formula, what was his basic concepts? The bed load he assumed to move in layers. The bed load is moving in layers. And how much thickness of the layer? Equal to small d, where d is the diameter of the sediment. This due to force exerted by the fluid. You know, the fluid is moving in this direction, having certain depth of flow. This may be the water surface, and this is the this is the bed of the channel here. This is the bed of the channel, and this is the water surface, and the water is flowing in this direction. So when water will flow in this direction, it will apply a shear stress on the bed in this direction, due to which the layers of the bed, they will move like that. The upper layer will move with the highest velocity. The lower layer will move with a velocity lesser than that, and the next layer will move with further lesser velocity, and then the next layer further next velocity, less velocity, and maybe the first layer is not moving. So if you will see that this distribution, velocity distribution of the layers, that velocity distribution is linear, and it is, increasing as we move up. So here it is mentioned that the velocity of the layers is assumed to vary linearly by equal increments from 0 to maximum. So this is the first layer, the second, third, and with what velocity the second layer is moving with delta V. The third layer is moving twice of delta V, then 3 of delta V. Nth layer is moving n minus 1 times delta V. So this concept was given by the device while deriving his equation to compute the bed load transport rate. So do you have any question here? Any questions? And what is this one? This is the velocity distribution. And here the velocity of flow is maximum on the surface and the lowest at the bed of the channel. So now I want to show you the movement of the bed of the channel in an experiment. So that I want to open another file. And okay, now I would like to unshare this presentation and would like to share that video. Where is that? Yeah, here. Is it shared? Please let me know.
Is it not yet?
Not yet shared?
सर स्क्रीन शेयर हो
Yes, sir.
गई वीडियो में?
Yes,
वही,
sir, अभी वीडियो नहीं।
yeah, screen share पे are you watching some experiment in lab?
No, sir.
Okay, then wait. All right.
फोल्डर भी हो रहा है सिर्फ,
क्या हो रहा है?
हमें फोल्डर नजर आ रहा है जिसके अंदर फाइल्स पड़ी हुई हैं, डुबॉइस बेड लोड और ग्रेवल बेड लोड।
अच्छा, कोई नहीं don't worry. I will try to share it again. Share नहीं हुई ना proper. एक्चुअली ये पूरा फोल्डर नजर आ रहा है आपको?
यस सर।
तो अब ये नहीं नजर नहीं आ रही? वीडियो
यस सर वीडियो नजर नहीं आ रही.
वाई? तो वीडियो शेयर नहीं हो रही, इट मीन्स why it is not now? Not yet?
No,
No,
sir.
sir.
Yes, sir. अब नहीं हो रही.
ये क्या? Yesterday. Okay, I don't know what's the reason. Actually, again, even not now.
No, sir. सर आप entire screen share करें फिर शायद share हो जाए.
Acha, okay, I will try once, and if not possible, then acha, entire screen. Okay, dear, then I think we leave it. All righty, I think there is some issue. I will share this video with you, which will show you the basically bed load movement in a laboratory experiment. And that movement is very similar as perceived by the device. What the device says. device क्या कहता है? हाँ जी? क्यों भाई दुबई क्या कह रहा है? How the bed load is moving? Dubai says that bed of the channel moves in layers. The first layer, which is the lowest layer, it doesn't move, but the upper layers, they move with velocity, and as we move up, the velocity of the layer is higher as compared to lower layers. And this velocity distribution is linear and increasing as we move up in the bed of the stream or channel. Okay, ji? Can you see this slide?
Yes,
Slide
sir.
to nazar aa rahi hai? Okay, then we will continue and I will share that video with you through email and you can check yourself. I don't know what's the issue. Now we want to discuss the bed load formula given by the Dubai. So Dubai formula is this one, which is given in equation number 1. So QS, what is QS? This is the bed load transport rate per unit width of the channel. I think you remember small q, which we studied in hydraulic engineering. What is small q?
Discharge per unit width.
Very good.
Specific.
Discharge per unit. Yeah. Now what is this QS? This is the sediment discharge. Which sediment discharge? Sediment discharge in bed. Yeah, bed load sediment discharge per unit width of the channel. QS, which here it is given. Huh? What is the CS? CS is the parameter depending on several sediment characteristics. What is the gamma? We know very well it. This is the specific weight of. Who's the specific
Water.
weight?
Water.
Good. And this is the Y. Y is used as depth of. What is Y?
Slope.
Depth of
Yes.
flow.
Depth of flow. This is in feet, huh? And S is the slope of the bed of the channel. Usually we design these channels for which flow? Non-uniform flow or for uniform flow?
Uniform
Normally in our irrigation channels, the flow is uniform. And when the flow is uniform, the slope of energy line is same as water surface slope, and it is same as yes, it would be same as
Bed of the
bed
channel.
slope of the channel. है ना? So this S is bed slope. What is SC? SC is the yes, critical slope. What do you mean by critical slope? वो कौन सा slope है जिसको हम कहेंगे critical slope? This is not that critical slope which we studied in hydraulic engineering. That was the slope to achieve to achieve what?
So critical flows chief
Minimum specific energy.
Yes, sir.
For the given discharge per unit width, है ना?
Yes, sir.
या maximum discharge per unit width for the given specific energy. That was something else. This is the critical slope with reference to sediment transport. So yeah, what is this SC?
So
The channel
slope
slope at which sediment transport begins. Yeah, at which sediment particles on the bed, they are in critical state. What is critical state? It is just balance state. You know, if you consider a sediment particle on the bed of the channel, so there are some forces which are called as opposing forces, which are hydrodynamic forces, which is the drag force, etc. So it tries to move the sediment particle and we call it opposing forces. The second are the resisting forces. That is the submerged weight of the sediment. So that weight resists the movement. And you know, when these two forces, the opposing forces and the resisting forces on a sediment particles, when they become exactly equal, that state is called of the motion is called as critical state. And the slope which gives us for a given discharge, which gives us this condition, is called as critical slope. at which a sediment particle is just stable. If the velocity of flow is slightly increased, then what happens to the sediment particle which is on the bed?
They start moving.
Yes, then it should start moving. So SC is that critical slope. Is it clear? Now the Chassis equation we can use according to Chassis equation. The small q is equal to c y raised to 3 by 2 s raised to 1 by 2. You can easily derive this. The capital Q is area into c under root rs. And what is small q? The SAR per unit width. And here, instead of using hydraulic radius, we have used the depth of flow. We are assuming that the channel is wide. Okay, now what is the CS, which is a coefficient based on sediment parameters, and this is given by Straub. Straub was another engineer, hydraulic engineer, who has proposed this value of the CS. He says that CS is 0.17 over d power 3 by 4. And what is the d? Sediment diameter in the bed in millimeters. Of course, average sediment diameter and RD50. So if we have the diameter of sediment in the bed, we can compute CS. What then SC, which is the critical slope. This equation is also given by Straub. And he says that the critical slope for a channel is equal to 0.00025 small d plus 0.8 over ym, where ym is the mean depth of flow in the channel. So if it means we can compute the critical slope of the channel at which the sediment particle on the bed is in critical condition. So the above equation 1 we can rewrite like this, QS over Q, because we have the QS, we have the Q, so dividing this equation by this, so you will get this expression. So what is QS over Q, by the way? Who will tell me? What is the
ratio of
Hanji?
sediment discharge with ratio of
Sorry?
sediment discharge per unit width to water discharge per unit width.
Yeah, that it appears like that, but what is another parameter? This QS over Q, yeah, capital QS over capital Q. You know, the sediment discharge over water discharge. This is the sediment concentration. Okay. So this QS over Q would be sediment concentration of bed load, because we are just considering the bed load. We are not considering suspended load right now. Is it clear? So QS over Q is the sediment concentration. Okay. Now using Manning's equation. So if you will use Manning equation and V is equal to 1 over N R raised to 2/3 S raised to 1 by 2. As we are using which system? कौन सा system use कर रहे हैं? Which system we are? System of units.
FPS.
English
system.
है ना? So yes, what is the Manning's equation for English system? V is equal to 1.49 over N R raised to 2/3 S raised to 1 by 2. And by substituting values, we will get this equation of velocity of flow. And now we have one example to be solved by this rational method using device equation. Now the problem is given in the book, and he says that design an unlined earthen channel to carry a discharge of 60 Q6 with a bed load 100 ppm. So what is this given? 100 ppm. What is 100 ppm? ppm means parts per million. Means 10 raised to power minus 6. And bed load 100 ppm means it is the sediment concentration which is given. So it means it is given QS over Q is 100 ppm. Mean diameter of bed material is 0.25 millimeter. So small d is 2.25 millimeters. Now how we have to solve it? By using the rational method and the bed load equation which we are using, Dubai's. So we have to, first step is we have to assume certain depth of flow. Let's say D we are assuming as 2.5 feet. Then compute the critical slope by using Straub's equation, which is this one, putting values, you will get this answer for the critical slope, 0.00014. And then we have to assume this Manning's n, this may be small n, or 0.0225. And you know, we can see this Manning's n value by consulting any tables given in the books, standard books of irrigation engineering. Now we will use equation which is given by the device to compute the bed load transport rate, QS over Q and so on. By substituting values, you will get the S. You can compute the S because in this equation, everything is known. And if the D or Y, we can assume, yeah, D or Y is the same thing, huh? And Y, if we are assuming, then we can design the longitudinal slope of the channel. And we have computed longitudinal slope of the channel as 3 into 10 raised to power minus 4. Is it clear? Now we want to use yes, please.
Depth और n की वैल्यू किस बेस पे assume की है सरकार ने?
Yes, that's very good question. That depth of flow value, basically we have assumed that how much discharge the channel has to carry. Is it okay? Because the discharge is very less, 60 cusecs, so depth of flow should be lesser. But if we want to design it on 600 cusecs or 1200 cusecs, we should assume a bigger depth. But you know, whatever the depth you are assuming, and accordingly you are designing a channel, and finally you are getting the dimensions. And at that stage, it looks that, oh, these dimensions are not so good. These dimensions doesn't look nice. So then you can revise. Then you can again assume another value of the D, and then the other dimensions will be computed accordingly. Now your second question was on what basis the Manning's n was taken or is selected. The Manning's n value is selected on the basis of the material of the bed end sides and you know its quality. Is it smooth or is it rough? And that we will discuss in one table. Then I will let you know. What is your name?
Shehbaz Zafar.
Huh?
Shehbaz Zafar.
Shehbaz. Okay, Shehbaz, I will remind you and will let you know that one of the table is that which you can consult for determining the or taking the value of Manning's n. So, okay, shall we move now next? So we got this value of the longitudinal slope. जी भाई.
सर ये SC की जो वैल्यू आ रही है 0.00014, इस तरह तो मतलब 1 in 7000 आ रहा है तकरीबन. तो ये इतनी मतलब इतनी कम स्लोप हमने प्रोवाइड करनी है इसके लिए फिर.
Yes, you know these जो channels हैं in the alluvial soils, they have very gentle slope. They do not have very steep slope. ठीक है?
Okay, sir.
That is in hilly areas. We can keep high slopes, but in alluvial soils, over slopes are very gentle. Okay,
Sir,
now we have
sediment.
जी
सर सेडिमेंट मूवमेंट फिर इतनी कम स्लोप पे पॉसिबल है?
That's why that we are considering. We are using a bed load equation, and we are designing just at the critical state. That जो critical slope था that we have computed, and which slope is greater? ये 0.0001 ज्यादा है या ये ज्यादा है?
ये बेड कंसंट्रेशन से जो है 0.0003 सर, ये जो बेड कंसंट्रेशन से है 0.0003 सेडिमेंट सॉरी सर कंसंट्रेशन से।
हाँ ये वाली दिस इज
सर
सेडिमेंट
कंसंट्रेशन।
मैं नहीं समझा
सर,
आपका सवाल, कैन यू रिपीट इट?
सर आई अंडरस्टैंड, बट आपने पूछा था कौन सी ज्यादा है, तो मैं बता रहा हूँ कि ये डाउन वाली ज्यादा है, 3 × 10⁻⁻⁴।
ये ज्यादा है?
यस।
ओके, ऑलराइट, सो इट मीन्स या तो फिर इसकी कैलकुलेशन आप दोबारा चेक कर लें, मे बी देर इज सम इशू, और it should not be more than. We have to keep the longitudinal slope slightly less than this critical slope. Then it will not move. Okay?
Okay, sir. Thank you.
Now compute the velocity of flow by using this equation and putting the values here. The velocity of flow you will get as 1.75 feet per second. And once we know the velocity of flow and we know the discharge which the channel is carrying, so we can compute the area of flow required to pass this much discharge. So discharge over velocity. So you are getting 34.1 square feet area of the channel. Now you have to assume certain side slopes, 0.5 and 1, and assuming certain side slopes, then we have the equation of area like this: BD plus 0.5D square, as we have already assumed the D and the area we have. So there is only one unknown, which is the B. So B you can compute as 12.4 feet. And the slope is this, and accordingly this channel is being designed by the rational method using Dubai's equation. All right, just please try to learn these steps, but you please check all calculations again.
Okay, sir.
So now we want to discuss some classical methods, rational methods for the design of stable channels. Those classical methods are two. One is the permissible velocity method, and second is the tractive force method. You know, previously by using Dubai's equation, we have used the basic concepts and then we designed a channel. But the widely used methods, rational methods, are these two: permissible velocity method and tractive force method. Now we want to discuss first the permissible velocity method. What is the permissible velocity method? In this, the channel size is selected such that the mean flow velocity for design discharge under uniform conditions is less than permissible velocity. Whatever is the permissible velocity, we have to keep velocity of flow less than that. And what is the permissible velocity? What is its definition? So permissible velocity is defined as the mean velocity at or below which bottom and sides of the channel they are not eroded. How they will not eroded? no sediment on either on the bed or on sides will move. So that velocity is permissible, which is the allowed velocity in a channel. So permissible velocity in a channel, it depends on the type of soil, size of particles, depth of flow, and curvature of the channel. How it depends on the curvature of the channel, that we will see just now after maybe few minutes. So from where we have to see the value of the maximum permissible velocities for different materials. So that those are given in table 4.4 of your textbook by Irrigation and Hydraulic Structures by Dr. Iqbal. Okay. And these values which are given in the table are for straight channels. And having how much depth of flow? 3.25 feet depth of flow. So it means you need to apply correction. If the depth of flow of the channel which you are designing is different as compared to 3.25 feet, then you have to apply a correction factor, K. And also you have to apply a correction factor if the channel you are designing is not straight. So if the channel is curved, then you have to apply a correction on the permissible velocity value, which you are obtaining from table 4.4. Now I would like to show you table 4.4. So this is the table 4.4, permissible velocities. These are the various materials of the bed and banks of the channel, like fine sand colloidal, sandy loam, silt loam, non-colloidal, ordinary firm loam, and coarse gravel, etc. And here the Manning's N value, they are also given. So Shahbaz,
Yes, sir.
you asked me how to select value of Manning's N.
Yes, sir.
Okay.
I get that. Yes, sir.
Huh? Now you can see, but for several materials of the channel, the value of Manning's N varies from 0.02 to 0.025. क्यों जी समझ आ गई?
Yes, sir. Yes, sir. Yes.
तो अर्धन चैनल चलिए Manning's N कहाँ से कहाँ तक लेते हैं? 0.02 से 0.025. Depends on the material type. But again,
Yes.
it also depends on the condition of the bed and banks. अगर बहुत खराब हो गई है तो the Manning's N value we will take higher, otherwise lower. अच्छा, now come to the permissible velocity. These values are given for permissible velocities when the water in the channel is clear. What about the water which is flowing in our canals? Is it clear or is it turbid water? Like in Lahore branch canal.
Turbid, sir.
This is turbid water. There is a lot of silt which is in suspension in the channels. So water is silty, okay? And if the water is silty, you have to take these values of the velocities. Moreover, hydraulic shear stresses are also given in this table. So for clear water, what is the material which can sustain highest velocity of flow? Highest कितनी है भाई?
6 for shields.
6 feet per second. 6 feet. This is the highest permissible velocity in the channel. For which type of the material? Shales and hard pans. This is a very stiff soil. In that case, we can assume. But you know, for sandy loam, the value is only 1.75 feet per second if the water is clear. But if the water is silty, we can take 2.5. So this is how this table you have to consider. But the values of the permissible velocities which are given here, they are for a depth of flow is how much?
3.5.
3.25 feet.
Oh.
And if the depth of flow, what the channel which we are designing is different, then we have to apply a correction factor K. Moreover, if the channel which we are designing is straight, then these are the permissible velocities. But if the channel is in curvature, then we have to reduce these permissible velocities by some factor. Okay. Now we will go back. I will go back here. For other depths, apply correction K. Now how I can see the correction factor K? For other depth, find value of K by consulting figure 4.8. Now I would like to show you figure 4.8. This is the figure 4.7 on left hand side. This one is the figure 4.8 on the right hand. Is it right hand? Huh? This is the right hand side. And what is the variable on y-axis on this figure 4.8? क्या value है? क्या चीज है? कौन सा variable है?
Average depth.
Average depth.
Average depth of flow in feet.
Depth.
And GG. Okay. And what is the variable on x-axis?
Correction factor.
Correction factor. Its value varies from 0.8 to 1.3. And you know, this is the one correction factor. At what depth it is? 3.25 feet. So we don't need to apply any correction factor because what is the value of correction factor? 1. Okay. But if I want to keep a, let's say 2 feet depth of flow, the correction factor would be 0.9. So the velocities which are given in that table, I have to reduce them by 10%. But if the depth of flow is 5 feet, okay? If the depth of flow is 5 feet, how much is the correction factor? 1.1. I have to increase those velocities by 10%. 1.1 means 10%. Okay, further we will go back. These values should be reduced. Which values? Which are given in table 4.4? Table 4.4. Yes. We have to reduce for sinus channels as given below. You know, if the channel is slightly sinus, then those velocities we should reduce by 5%. So factor क्या होगा? With which we should multiply with those velocities. 0.95. 0.95. If it is moderately sinus, then 13% we have to reduce velocities, and if it is highly sinus, then 22% velocities we must reduce. It means the factor we should use is 0.78. Yes, good. Okay. Thank you, Ji, for muting. Now we want to discuss the design procedure for this irrigation channels using permissible velocity approach. Now these are the steps. What is the first step? Permissible velocity is determined from table 4.4, as I have shown you already that table. And if you need to apply corrections, you have to apply 2 corrections, one for depth of flow, the other for curvature. Okay, this is the step number 1. It means you have simply selected the value of permissible velocity. What is the step number 2? Area is found from equation. The area is discharge over velocity. All right, so this is the cross-sectional area of flow. What is the step number 3? Is assume a longitudinal slope S, maybe from natural topography, etc. So this you have to assume. And then assume a side slope based on, side slope depends on what? The side slope of the channel.
Angle of repose of soil.
Yes, very good. Angle of repose of soil, and our side slope should be slightly lesser than the angle of
soil type.
And also we have to assume Manning's N. From where we can see Manning's N? From table 4.4. दे रहा है ना वो? And
Yes,
then
sir,
calculate
yes.
hydraulic radius R from Manning's equation. निकल जाएगा R, because we have area and we have the discharge is equal to area into 1 over n R raised to 2/3 s raised to 1 by 2. So the R hydraulic radius we can compute. Now the wetted perimeter is determined from, we know the area and we know the hydraulic radius, so A over R is the wetted perimeter. Now computed values are equated to expressions for P and A. What is the equation of A for trapezoidal channel? That is B D plus ZD square. यही होगा ना? This is the area.
Yes.
And what is the equation for wetted perimeter for a trapezoidal channel? That is the B, which is the bottom width, plus twice of sloping length. How much is sloping length? Under root of ZD square plus D square. Is it that?
Yes, sir.
Okay. So now we have two equations. And we have two unknowns. Okay. So it means the channel bed and depth of flow can be computed. So these are the steps to design the channel by using rational method. Any questions?
No, sir.
ये permissible
Okay,
values
now-
ये just experimental basis पे हैं?
Yes, of course. These have been determined in the experiments and flumes, very big size flumes, in which we could change the slopes etc, and we by changing the material in the bed and sides, and by physically examining the movement of sediment on the bed, that when a sediment particle is start moving from there, these velocities are basically recommended by the certain engineers and authorities. Okay, now we have one example. This is given in the our textbook. Design an unlined earthen channel to carry a discharge of 60 cusecs. It is the same discharge with a sediment load of 100 ppm. It is same as we solved a numerical by using Dubai's equation. Mean diameter of bed material is 0.25, and nature of silt is non-cohesive type. So this will help you in selecting the permissible velocity. Slope of ground is 1 over 1000. So you may take maybe this value as the bed slope. And then now you have to solve this equation. So this problem is solved on page 159 of the book. So this you have to see yourself. Okay. And now we have to discuss tractive force method. Shall we take rest? 10-minute rest?
Yes, sir. Why not?
Okay. Just have a 10-minute rest and then we will continue. क्यों जी, is break over? Okay ji, I think 10-minute break is over now. Are you online?
Yes, sir. Yes, sir.
Yes, sir.
Okay, very good. Zabardast. So now we want to discuss another method of rational approach to design the irrigation channel. That is the tractive force method. Now, what is tractive force method? In this method, and what is tractive force, by the way? It is mentioned here. Tractive force, the force exerted by the water on the beds and side of the channel when the water flows. And this is due to the shear stresses. Actually, when the water flows in a channel, it exerts shear stresses on the bed and sides, and due to that, the force, shear force, which is exerted by the channel is called as tractive force or hydraulic shear stress. Is it clear? And what is equal to this force? This force for uniform flow, it is equal to the component of the weight acting in the direction of flow. And how we can compute this tractive force? Tau naught is gamma r s naught. R gamma y s naught, and this you know that we replace R with Y if the channel is wide. Then what is the tractive force method? So in this method, scour and erosion process can be viewed in a rational way by considering forces acting on particles lying on channel bottom or sides. The channel is eroded if resultant of forces tending to move particles, they are greater than resultant of forces resisting the motion. Similarly, if the opposing forces, they are more than the resisting forces, then the particle on the bed has to move. And if the opposing forces, they are lesser as compared to the resisting force of the sediment particles, then the sediment particles on the bed, they will not move. So this concept is referred as tractive force approach or the hydraulic shear stress approach. Is it clear? Now, what about the distribution of tractive force? Do you think that the tractive force acting on the bed and the tractive force acting on the sides is same? What do you think?
No, sir.
Yes, which one should be lesser? The
On the
tractive
sides.
force which is acting on
The sides.
sides. Why? Because as we move up the depth of flow, what happens to the depth of flow when I am here? Only this is the depth of flow, right? So depth of flow is smaller on the sides. Moreover, they are at certain angle. So the tractive force on the side is lesser. But what about at bottom? So they have high hydraulic head or depth of flow. So the tractive force, if the tractive force on the bed of channel is equal to this gamma ys naught, so roughly tractive force on the sides is 75% of the tractive force which is acting on bed. Is it clear?
Yes, sir.
So how much is the tractive force on the sides? 70.75 of gamma ys. Now the reduction factor for channel sides. So reduction factor, which is also called as tractive force ratio, for critical tractive force on channel sides, we can say that K is the tractive force on side slope, and critical tractive force, this ratio is called as K, means this over that. So this is the tractive force on the sides, and this is the tractive force at bed. This is the 0.7 times gamma ys, and this is the critical tractive force. So this ratio K we can determine like this. K is under root 1 minus sin square theta over sin square phi, where theta is slope of the sides. ये जो slope है from with respect to horizontal. So this angle is theta and phi is the angle of repose of soil. And we know that this theta value should be lesser than phi, because this is the actual angle of side slope. So if we have this data, then we can compute K, and if this K is equal to this, then you know what we can determine. If we have the value of this critical shear stress or tractive force, and it means there are only two variables, y and longitudinal slope. And suppose if the longitudinal slope is known, then we can determine the depth of flow. And if by assuming the depth of flow, then we can determine the longitudinal slope. Is it clear?
Yes, sir.
Okay, now what is the critical tractive force? The force at which channel material begins to move from a stationary condition is called critical tractive force. Actually, critical tractive force, again, I would like to explain that. So it is that tractive force or that hydraulic shear stress at which the sediment particle is just in critical state. It means the opposing forces on this sediment particle, they are exactly equal to the resisting forces. So that state is called as critical state, and the tractive force at that state is called as critical tractive force. Okay, so critical shear stress for cohesive and non-cohesive materials is given in figure 4.10 and 4.11. The values of critical tractive force we have to take from these two figures. These values are for straight channels and should be reduced for sinus channels as given below. Slightly sinus, it must be reduced by 10%. Moderately sinus, it should be reduced by 25%. Highly sinus channels, it should be reduced by 40%. It means whatever the value we will see from that figure, we will use 0.6 times that value. Now we want to see the figure 4.10 and 4.11. These are those two figures. These figures are given in our textbook, Irrigation and Hydraulic Structures by Dr. Iqbal Ali. So this one is the figure 4.10 and this is the figure 4.11. This figure gives the value of permissible unit tractive force, या critical tractive force for canals built in non-cohesive soil. What are non-cohesive soils? जी
जिसमें कोई नहीं होती जैसे सैंड वगैरह
कोहिजन नहीं होती।
Sand.
कोई मिसाल दो मुझे, किसमें कोहिजन नहीं होती?
तो सैंड में नहीं होती
और
सीढ़ी पे भी नहीं होती है
क्ले में कोहिजन होती है ना?
यस सर।
Gravel.
ग्रेवल में कोहिजन नहीं होती, सैंड्स में कोहिजन नहीं होती। सैंड, ऑल टाइप ऑफ सैंड, कोर्स सैंड, मीडियम सैंड, फाइन सैंड, है ना? सिल्ट्स, कोर्स सिल्ट्स, दे हैव आल्सो वेरी लेस या नेग्लिजिबल कोहिजन। तो क्ले में कोहिजन होती है। अच्छा, ये जो टेबल है 4.11, इफ द मटेरियल ऑफ द चैनल कौन सा है? cohesive soils हैं. Cohesive soil means basically there's a mixture of clay is also present, maybe with silt or with sand. Okay. Sometimes you may not find pure clays. Normally pure clays नहीं होती है ना, तो वो maybe sandy clay होगी, silty clay होगी. All right. Now come here, figure 4.1. What is the y-axis of figure 4.1? Permissible unit tractive force in pound per square feet. What is the variable on x-axis? Average particle diameter in millimeters. So this is the diameter. How many graphs are given? 4. Graph number 1 is recommended values for canal with low content of fine sediments. So this is this figure. Actually, and this graph 2 is for canal having high content of fine sediment. And graph 3 recommended values for canal with clear water. But actually you see that this is for clear water, this is for high sediment, this is for low content of silt. So it is like that, huh? And number 4, this curve is for coarse non-cohesive material. % larger, I mean of larger size sediments are there. Maybe it's 25% part is larger. And you see that this is for which type of sediments? For coarse sediment, 5 millimeter से लेकर maybe up to 100 millimeter. It's a very coarse. This is gravel bed, है ना? But this is the alluvial beds. And now, for example, if my canal has very low content of fine sediments in water, so I have to consult graph number 1. And I have to see that what is the bed material size. And accordingly, this I have to find this value. So this is 0.1 something pounds per square feet, or PSF, is the tractive force, critical tractive force on which I have to design this channel. Okay. So what happens with the increase in diameter of the bed material to the tractive force? क्या हो रहा है जी? In all three curves, and even the 4th curve, with increase in diameter of the bed material, the tractive force, critical tractive force increases. ऐसे ही है? देखें यहाँ diameter है 7 millimeter. This is the value of tractive force. If it is 50, this is the value of the tractive force. Okay, but what is the range of the critical tractive force? भाई रेंज क्या है यार, यहाँ से देख तो लें. 0.01 from starting from 0.01 to आप यहाँ पे देख लें क्या वैल्यू है, maybe 1.5 PSF. So this is the range of tractive force. Okay, but anyway, you can select the value of tractive force. And now come to this figure. Now, if it is a cohesive material, then if it is very compact, and then fairly compact or loose. So here the material is loose and it is getting compact in this direction. So what happens to the critical tractive force? So critical tractive force in the cohesive material, that it increases with increase in compactness. Is it true? देखें यहाँ ज़्यादा compactness है, we have a higher value of the critical tractive force. So again, if it is lean clay soil, clays, heavy clay soils, sandy clays. So among the clays, which has the more value of the critical tractive force? You know, for any one value of this soil type in the bed, तो फिर भी sandy clays के लिए अलग curve है, so it gives a higher value of the tractive force. I think now everything is clear that how we have to select the value of the tractive force, and the value of the tractive force यहाँ पे कितनी highest value है 1 psf है ना. It means कि जो value of tractive force practically in these channels and you know these are alluvial channels, तो कितनी value है जी tractive force की यहाँ पे जो cohesion less non cohesive materials हैं, its value is simply 0.2 psf, very small value of the tractive force is available. Okay, now how we can determine the angle of repose of the soil. So this is the graph for angle of repose of soil. Y variable on y-axis is the angle of repose with horizontal, and x-axis is the particle size in millimeters. Actually, I think this is a mistake, and this is 0.124 millimeters. And what is the general relationship for the angle of repose of soil with increase in diameter of sediments? क्या होता है? Increase in diameter of sediment in the bed. What happens to the angle of repose of a material? It increases. Sediment के diameter बढ़ने से angle of repose भी बढ़ रहा है.
Increase.
Okay.
Yes.
That is it. And you know, for a particle size of about 4 millimeter, all lines they become almost horizontal. Okay, so it means these are the maximum value of angle of repose. Now, what are these graphs? 1, 2, 3, 4, 5. One is very angular. Angular का क्या मतलब है? Particle shape बड़ी angular है. Then number 2 is moderately angular. Number 3 is slightly angular. Number 5 moderately rounded. अब roundness शुरू हो गई. Number 6 very rounded. So this is very rounded. This is for round. Rounded means spherical shape of particles, sediment particles, which are on the bed. So what happens to the angle of repose of the soil for a given value of the, let's say 1 millimeter मैं ले रहा हूँ, या 0.4 millimeter ले लें. For 0.4 millimeter diameter, what happens to the angle of repose with angularness? जैसे angular बढ़ेगी, angularness of the particle, there is an increase in angle of repose. और जैसे ये rounded होगा, the sediment particle, as it will move from angular to roundness, the value will reduce of the angle of repose. Is it clear? So angle of repose is a function of two things. Number one is the size of sediments, and number two,
shape
of sediments. ठीक है ना? तो साइज के बढ़ने से क्या हो रहा है एंगल ऑफ रिपोज को? It increases. और शेप एंगुलर होने से क्या हो रहा है? Again the angle of repose is increasing. ठीक है ना? So this one is angular, very angular, highly angular size of the sediments है, और यहाँ पे maximum कितना है भाई? Angle of repose of the soil 41 क्या? 41 degrees. Okay. So lowest angle of repose is this one. कितना है? 21 डिग्री. 21 degree. So we must have an idea that what is the range of angle of repose. 21 degree से 41 degrees is the range of angle of repose. All right. Now what is the design procedure? What is the first step? Permissible या critical shear stress is found from the figure 4.10 and 4.11 depending on the material, है ना? अब वहां से आपने वो वैल्यू पिक कर ली. Then you will apply correction factors K for channel side slope and angle of response, angle of repose is determined. Angle of repose that we can determine from this figure. This is the figure, actually number I have deleted, but anyway, this is the same book figure. Then the unit tractive force on the side, which should be 75% on the bed, is equated to the product of permissible shear stress and reduction factor to compute depth of flow for the given slope. This is the basic equation. So this value of the K, so this K we have already determined, and using this equation and assuming certain slope, we can compute the depth of flow. Okay, for a given S naught. Now the bed width is determined from Manning's equation, and this is how we can design a channel using tractive force method. And then there is an example on page 168 in our textbook. It is a solved example, so you have to see it. The data is same. Now the discharge is 62.6. Bed slope of the channel is this, and the particle is the same as 0.25 millimeter, and is of the non-cohesive type bed sediment. All right, so this you will see yourself from the book, and please try to understand and solve it manually. See from book, but you have to solve it manually. And with this, we have finished this chapter number 1, which is the design of irrigation canals. So till now, what we have discussed, we are able to design a lined irrigation channel as well as we are able to design unlined irrigation channels. For unlined irrigation channels, we know the both approaches. First is the empirical or regime approach, and the second is the rational method. In the empirical method or regime methods, we have further discussed 4 methods. Number 1 is the Kennedy method. Number 2 is the Lacey's method. Number 3 is the Blanch method, and number 4 is the Simons and Albertson method. Whereas in case of rational methods, we have discussed the design of channel by taking the basic equation of barrel load transport like Dubai's, and then we discussed the 2 classical methods. One is the permissible velocity method, and second is permissible tractive force method. And with that, we are concluding this chapter. So if you have any questions, you are welcome. Yes.
Sir?
Yes.
तो एक क्वेश्चन था कि अब जो अगर हम सेडिमेंट्स की बात करें, आपके लाउड
Yes, yes. जी जी.
तो उसमें यह था कि 2 तरह के मटेरियल्स होते हैं कि एक होगा आपका बेड मटेरियल, सेकंड द सेडिमेंट्स दैट आर इन सस्पेंशन विद इन वाटर. तो हम इस चीज को कहां पे
Actually, there is some disconnectivity in your voice. Can you repeat?
सर मैं कहते हैं सेडिमेंट्स
Again, there is disconnectivity. So your mic is off, I think.
सर मैं बाद में
फिर बंद हो रही है आपकी आवाज. Anyway, okay, now I would like to unshare this presentation and want to start a new chapter. which is this chapter number 2 from my side. And what is the name of chapter? बोलो भाई क्या नाम है? कोई नजर आ रही
Sir,
slide?
low head diversion barrages.
Low head
Low
diversion
head
dams.
diversion dams or barrages. Okay, so that is our second chapter, and I would also like to share these all presentations with you. So I need your email group. वो ईमेल ग्रुप को जो ग्रुप की ईमेल मुझसे शेयर कर लें तो मैं उस पर ये भेज दूंगा. ओके, बिकॉज नाउ द ऑफिशियल correspondence channel is email. We will try to avoid WhatsApp as per notification of UET. Okay, canal headworks or diversion headworks. What is a canal headwork? Does anybody know? Have you ever heard canal headworks? Yeah, diversion headworks, yeah, simply headworks.
Yes, sir.
What is headwork?
Sir, headwork is
Headworks. This is plural. ये अकेला नहीं
Yes,
लिखेंगे
sir.
हम work. What are headworks? Yeah, what is
Sir,
meant by headwork? Yes.
So it is a kind of a structure which is usually provided over the main channel in order to divert the water and also raise its level.
Yes, simply headworks means all works which are constructed where?
Sir, main channel.
At the head of main canal.
Yes,
कहाँ
sir.
पर? At the head.
Head
कहाँ होता है?
head.
सबसे ऊपर है ना? Canal, main canal का head कहाँ होगा? It is taken off from the river. It is off taking from the river. So all works which are constructed at the head of the main canal in the river, for what purpose? To raise the water level and to divert that water towards the canal. Those are called as headworks. Is it clear?
Yes, sir.
Okay. So what is the difference between headwork and a barrage? कोई फर्क है या एक ही चीज है?
Sir, the main difference between the barrage and headwork is the ponding effect.
Yes.
Sir, basically in barrage, we have the gates, and if
yes, we have actually barrage is a special type of headwork. Okay.
Yes, sir. It's a modified form of the weir.
We provide gates, and the ponding obtained by gates is more than obtained by
the
crest.
height of the yes, the height of that because
yeah, that is the difference between headworks and canal. So every barrage is a headworks. Every barrage is a headworks, but every headwork
is not a barrage.
May be a barrage. Now I can give you an example. There was Khanki headworks. Have you ever heard Khanki? Khanki headworks.
Yes, sir.
It is on River Chenab, and now that headwork is reconstructed very recently, and its name is Khanki Barrage. Previously, it was not a barrage. It was only a headwork. Okay. Now come to the weir. What is a weir? Weir we have studied in the subject of hydraulic engineering. That is a streamlined wall built across a channel or a stream or a river, and it's a low head structure, And what is the purpose of weir? Its purpose is to raise water level up to required level. And why we want to raise the water level? To divert that water towards the main canals. And conceptually, we know that what is a weir? Weir is that hump whose height is greater than, उसकी height किससे ज़्यादा होती है? Critical height. Because then weir will, that hump will cause damming action on upstream side. All right. But if the height of the hump we keep lesser than the critical hump height, it will simply call as hump. Okay, and not the weir. Now, difference between weir and barrage. Now, what is in this figure? Figure A, weir without shutters. There are no shutters are provided. And total ponding is being carried out by the crest of the weir. So this is the total ponding. And no ponding is carried out by the shutters. If you will see figure B, so this is the weir with shutters. But the dominant ponding or the major ponding is carried out by the crest of the weir and not by the shutters or gates. So ponding carried out by the gates is smaller as compared to by the crest height. So these both structures are weirs. These are not barrage. Is it okay? So the same is mentioned here. If the major part or the entire ponding of water is achieved by a raised crest like this or this, and a smaller part or nil part like this here, nil part is by the gates, of it is achieved by the shutters, then the barrier is known as a weir. आगे चलें. Now this is a barrage. So what is a barrage? If most of the ponding is carried out by gates and a smaller or nil part of it is done by the raised crest, then the barrier is known as a barrage or a river regulator. River regulator. Regulator, we have, the regulators of the fan. What do we with that? We change the speed of the fan. So here, river regulator, we change the discharge on downstream by these gates. Is it clear? Now you see this is the crest, this is the weir, and this is the crest of the weir. So this is the ponding carried out by the crest of the weir, and this is the ponding P2 is carried out by the shutters or gates, which is more than this. So this structure is called as barrage. So this is a barrage with small raised crest. Here, this is again a figure of the barrage with any raised crest slightly, but the main ponding is done by the gates. So that is a barrage. I think if it is clear, then we should move forward. Now we have to discuss barrage, a low head diversion dam. So if a weir is provided with gates, and how gates? The ponding achieved by gates is more than as achieved by the crest of the weir. To raise further water level, then such a weir is called a low head diversion dam or barrage. Is it okay, Ji? Barrages do not require strong foundations. What do you mean by strong foundations? जी कोई बताएगा? What is meant by strong foundations?
Yes, sir. Strong foundations means that the underlying strata should be rocky. It should have good
yes,
strength.
very good. Yes. It means the strata on which our structure is resting, that is rock.
Yes,
but in alluvial rivers, we do not have rocks, and if we have rocks, those are available at too deeper depths. So normally we don't provide barrages to that much depth, and we provide on the alluvium, means maybe sands or the fine silts. So these barrages rest over there. When we provide or we construct these barrages over sandy foundations, then what happens? In addition to surface flow, subsurface flow also takes place, and water also moves under the barrage. Okay. And once the water moves under the barrage, so it will also apply the uplift pressure to the barrage body. Hence, a barrage has to be safe against both conditions. What are both conditions? Number one is the surface flow condition, and the second is subsurface flow condition. Yes. If you have any question, do you have?
No,
sir. Okay.
No, sir.
Now, what is the purpose of barrage? We know that the purpose of barrage, first purpose is to raise the water level in the river so that it can reach to the proposed irrigation area. So we must raise it up to certain level. We have to fix certain pond level of the barrage. So on what basis we fix the pond level? It depends that how much area we want to irrigate. So how much we need the command or head. Okay. What is the second function? To divert the required quantity of water from the river to the main canals, maybe on one side or both sides, and to allow proper silt control. So we control also the silt entry into the canal, because if too much silt will enter in the canals, what will happen to the canals? That silt will deposit on the bed and sides of the canals, and then the cross-sectional area of the flow that will reduce. What is the fourth function? To provide permanent headworks for the canals in order to protect them during floods. You know, when the heavy floods they come, they cross this barrage structure, then what we do, we close the gates of the head regulator of main canals. It means we stop the supply of water towards the canals. Why? Why?
Sir, if we allow the flood water to go into our main canals, then it will invade the surrounding areas. So,
then what will happen?
so it will enter into the surrounding areas. It may
No. Actually, that is not the reason. When there are floods, so river water carries a lot of sediments. Their diameter is also bigger, and their quantity, silt load and silt grade, both. Silt, बल्कि silt नहीं, वो sand भी आती है, gravel भी आती है in case of heavy floods. So if the canal gates are not closed, then what will happen? Those heavy silt particles, in which there are sand particles, there may be gravel particles, those will enter into the canal, and what will happen? The slope of the canal is not such that to carry those sediments, to transport those sediments downstream. So those will settle down, and the cross-section of the canal will be silted up. Okay. What is the fifth function of a barrage? To provide better water regulation than a weir, because we have gates, so we can regulate how much quantity we need in the canals. So we will only divert that much, The rest of the water we will allow to move downstream in the river, downstream of a barrage. That is the purpose of a barrage. Is it okay? आगे चलें?
Yes, sir.
Okay, this is the
Yes,
last
sir.
slide. Today's last slide. We will discuss what are the components of a barrage. So here you can see that the major components of a barrage are these 11. Number one, main barrage portion. Main barrage portion means the whole weir. That is the upstream concrete floor, upstream glacis, crest of the weir, downstream glacis, and the downstream concrete floor. That called as main barrage portion that I would like to show you here. Like this one is the main barrage portion. Okay. This. So this one here, if you see that this is the upstream concrete floor, this is the upstream glacis, this is the crest of the weir, this is the downstream glacis, and this is the downstream concrete floor. This whole is called as main barrage portion. And in the plan that you can see from here, so upstream concrete floor may start from here, you have this part, and then here this is the upstream glacis, here maybe the crest, here the downstream glacis, and here will be downstream floor. The number two are the sheet piles. There are three types of sheet piles: upstream sheet piles, intermediate sheet piles, and downstream sheet piles. Like here, you can see that here, maybe this one, here we have to provide a sheet pile. This is the downstream sheet pile as the water is coming from this direction. So this is the upstream sheet pile. And this and that, these may be intermediate sheet piles. Then inverted filter, which is provided between downstream sheet pile and downstream flexible apron. Sorry, so here you can see this is the longitudinal section of the barrage, or main barrage portion. So, and the inverted filters are here. These are the inverted filters. So this is the downstream end of the downstream concrete floor, and this is the downstream flexible apron. Flexible apron means these are very large stones or boulders which are provided here, and this one is are the inverted filters. What is inverted filter? That we will discuss in detail next lecture. The fourth is the flexible aprons, means these are the large stones which are provided on the bed of the river on both sides, on upstream side as well as on downstream side. And then the undersluices, so these are the base at extreme ends adjacent to the canal regulator. Then there is divide wall, then there are fish ladder, guide banks. So these are the guide banks. So this is the guide bank, and this is also a guide bank, as this is the direction of flow of water. So this is the right guide bank, and this one is the left guide bank. And then marginal bunds are flood embankments, if you will see here. So these are the marginal bunds. So this is the right marginal bund, and this is the left marginal bund, because if this is the direction of flow, so we have to stand here and facing the direction of flow. So this is on our right hand side, this is on left hand side. The next are the head regulator of the main canal, from where the water is being discharged into the canals. Then the scent control devices, maybe silt excluder and silt ejector. So these we will discuss in the next chapter. Silt control in the canals. So today we want to stop here. So thank you very much for your patience. And if you have any question, then you are welcome. Now I am taking your attendance. Okay, I took your attendance. Do you have any questions?
No, sir.
Okay, if you do not have any questions, I am stopping the recording. And thank you very much. Allah Hafiz.